Imagine a man so relentlessly crushed by the weight of his own intellect that he must chemically induce sleep every single night. Not for a brief period of stress, but for 28 agonizing years. He never misses a dose, because whenever the room goes dark and he closes his eyes, he is immediately haunted by the undeniable, apocalyptic mathematics that he himself dragged into the light. Welcome to Legendary Lives Unveiled, where we dissect the sweeping, tragic, and world-altering trajectories of history's greatest phantoms. If you are captivated by the dark intersections of fate, science, and the fragile nature of human existence, make sure to subscribe, like, and share this journey into the abyss. Our mission today is to completely unpack the immense moral agonies of Sir James Chadwick, the painfully shy boy holding the blueprint for global destruction. Born in 1891 in Bollington, Cheshire, a bleak, unforgiving village choked by the cotton spinning industry, his origins were devoid of inherited wealth or academic pedigree. His father was a humble cotton spinner, his mother a domestic servant. This was the brutal tail end of the Victorian era, an atmosphere defined entirely by profound financial precariousness. At just 4 years old, a devastating blow struck. His father lost his job. His parents were forced to uproot to Manchester to find work, leaving young James behind in the austere, working-class home of his maternal grandparents for several years. This early, painful separation forged a spirit that was intensely private, deeply serious, and fiercely self-reliant. Navigating a world with zero safety nets, his mind became his only shield. Rejoining his parents in Manchester, he won a highly competitive scholarship to the prestigious Manchester Grammar School. It was the golden ticket out of the soot and the struggle, until the hidden costs of poverty slammed the door. His family simply could not afford the small supplemental fees required for books and uniforms. The scholarship was painfully declined, yet Chadwick did not break. He pivoted. He attended the Central Grammar School for Boys, trudging 4 miles each way through the brutal northern English weather every single day. By the age of 16, his intellect was undeniable. He sat for 2 university scholarship exams and conquered them both. In 1908, he stepped onto the campus of the Victoria University of Manchester. And here occurs the critical pivot point of his entire life, and honestly, of modern physics. Chadwick fully intended to study his true passion, mathematics. But the enrollment hall was a chaotic sea of confusing signage, multiple lines, and swarming students. He accidentally stood in the wrong queue. He was waiting for the physics department. When he finally reached the front of the line after an hour and sat for the intake interview, he realized his monumental error. Any ordinary person would have simply apologized and found the correct room. But Chadwick was paralyzed. His shyness was so debilitating, his terror of social friction and sheer embarrassment so absolute, that he simply could not bring himself to admit a mistake had been made. The interviewer began asking him about physics, and the quiet boy just played along. Out of pure, crippling social anxiety, James Chadwick accepted a destiny he never chose. He became a physics major, entering the cutthroat, egotistical world of early 20th century academia. Chadwick had to survive under the booming, larger-than-life father of nuclear physics, Ernest Rutherford. Rutherford was loud, demanding, and possessed a terrifyingly sharp eye for raw talent. He saw through Chadwick's silence, recognizing a quiet, almost unbreakable tenacity. In his final year, Rutherford handed the fragile undergraduate a complex radium experiment. Devise a means of comparing the amount of radioactive energy emitted by 2 different sources, using 1 gram of radium as a baseline measurement. Rutherford, a man who had just won the 1908 Nobel Prize in Chemistry, confidently suggested a highly specific experimental approach. But Chadwick, looked at the geometry of the physical setup, analyzed the math, and realized almost immediately that the Nobel laureate's method was fundamentally flawed. It simply was not going to work. It would irreparably skew the radiation absorption rates. This was the ultimate test of character. He was an impoverished student on a fragile scholarship. Rutherford was a literal scientific god. Yet Chadwick's scientific integrity outweighed his fear. He refused to fake the data. However, his debilitating social anxiety meant he was still far too intimidated to walk into Rutherford's office and correct him. So, he chose a third path. Working silently in the shadows of the lab, Chadwick completely discarded Rutherford's instructions and meticulously devised an entirely new, workable method from scratch. When he finally presented the immaculate results, Rutherford wasn't angry. He realized the kid had outsmarted him, and he was profoundly impressed. This act of quiet, empirical rebellion became Chadwick's first co-authored paper, published in 1912. He let the unassailable truth of his data be his voice. It earned him first-class honors in 1911, a master's degree in 1912, and the incredibly prestigious 1851 Exhibition Scholarship. His golden ticket had finally arrived, allowing him to leave the UK for continental Europe. He chose Berlin in 1913, specifically to study under Hans Geiger. Geiger had just developed an early, highly sensitive version of his radiation detector. Before this breakthrough, physicists suffered through the excruciating method of sitting in pitch-black rooms, staring at zinc sulfide screens to manually count tiny flashes of light from alpha particles. Chadwick aimed Geiger's advanced new instrument at beta radiation. At the time, emerging quantum theory dictated a strict, predictable universe. Physicists strongly believed that beta particles, high-energy electrons, were emitted at discrete, quantized energy levels. Like falling down a staircase, the energy drop should be exact and uniform, creating sharp lines on a spectrum graph. But Chadwick's hyper-accurate data revealed a terrifying chaos. His data showed a ramp, not a staircase. He proved that beta radiation actually produces a continuous spectrum. The electrons were flying out with a huge, chaotic, unpredictable range of energies, some fast, some slow, and everything in between. And this shattered the most sacred rule of the universe, the law of conservation of energy. The missing energy seemed to simply vanish into thin air. The anomaly was so colossal that Albert Einstein himself walked into Geiger's laboratory to examine Chadwick's math. The smartest man on the planet stared at the results, totally stumped. Albert Einstein reportedly confessed, "I can explain either of these things, but I can't explain them both at the same time." It was a profound crisis that wouldn't be fully solved for another 20 years, ending only when Wolfgang Pauli hypothesized the existence of an invisible, ghost-like particle carrying away the missing energy, the neutrino. But the undeniable, experimental proof belonged to the 23-year-old James Chadwick. He was on the fast track to scientific superstardom, until the calendar turned to August 1914. The world violently erupted. World War I broke out, and Chadwick, a British citizen, was sitting deep inside the capital of the German Empire. Hans Geiger desperately warned his young protege, advising him to flee to a neutral country like the Netherlands while the trains were running and the borders were still open. But Chadwick suffered from a fatal scientific tunnel vision. Entranced by his beta spectrum maps, he essentially ignored the geopolitical collapse outside his window. He viewed himself purely as a scientist, completely separate from the political squabbles of kings and kaisers. The German military authorities absolutely did not see it that way. In November 1914, the police arrested him as an enemy alien. After 10 terrifying days in a Berlin jail, he was dragged to the Ruhleben internment camp near Spandau. Ruhleben was a purely Dickensian nightmare, an old, converted racecourse. Chadwick was locked inside a freezing former horse stable that literally still smelled intensely of dung, crammed with 6 men into a stall built for 2 horses. The brutal German winters were accompanied by horrifyingly inadequate rations, watery turnip soup, and incredibly dense, sawdust-laced bread. The malnutrition inflicted severe digestive agonies that would uniquely plague Chadwick for the rest of his life. Men around him succumbed to the psychological collapse known as barbed wire disease. Stripped of the university's prestige, isolated from the global scientific community, Chadwick's environment demanded an unfathomable evolution. He absolutely refused to let his brilliant mind rot in the cold. He organized a science circle among the interned professionals and academics, delivering highly technical lectures to keep their intellects sharp. But lecturing wasn't enough. He wanted to do experimental physics from inside a freezing POW camp. Driven by a quiet, non-threatening intensity, he somehow won the sheer curiosity of his armed German guards. They allowed him to set up a makeshift laboratory in a drafty corner of the stable. Then, he performed a miracle of scavenging. During the early 20th century radium craze, a specific brand of German toothpaste called Dormad was marketed to the public, absurdly promising to destroy bacteria and whiten teeth using the magic of a radioactive compound, thorium oxide. Chadwick somehow convinced his captors to go into town and supply him with this specific toothpaste. He meticulously extracted the radioactive thorium oxide to use as a raw source. He then gathered tin foil from discarded chocolate wrappers, bits of copper wire, and scraps of wood to build a crude, yet fully functional electroscope. Enclosed in a jar, the delicate tin foil leaves would repel each other under a static charge. When the radiation from the toothpaste ionized the air inside the jar, knocking electrons off the air molecules and turning it into a conductor, the electrical charge leaked away. As the charge bled out, the 2 pieces of tin foil slowly fell back together. By timing exactly how fast those candy wrappers drooped, James Chadwick precisely measured subatomic radiation intensity from inside a horse stable. He wasn't just tinkering. He conducted legitimate, publishable science on the ionization of phosphorus. In that freezing darkness, he even took another young internee under his wing, a British military officer named Charles Drummond Ellis. Chadwick mentored him from scratch, forging a mind that would later stand beside him as a highly respected physicist at Cambridge. By the time the armistice was signed in November 1918, Chadwick was finally released. He returned to his parents in Manchester, physically emaciated and permanently scarred, but possessing a mind sharpened into a disciplined, lethal instrument. He would soon reunite with his old master. But as he stepped back into the hallowed halls of Cambridge, he was about to collide with a mathematical wall that would consume a decade of his prime scientific life. A desperate, invisible hunt for a ghost particle that would ultimately unlock the fires of hell. Upon returning to England, James Chadwick discovered a fascinating reality. The sheer devastation of the global war had effectively paused all scientific advancement in nuclear physics. He simply picked up right where he left off. Ernest Rutherford, now the director of the legendary Cavendish Laboratory at the University of Cambridge, the absolute center of the physics universe, immediately brought his brilliant protege down to join him. Chadwick earned his PhD in 1921, became Rutherford's assistant director of research, and together, they began attacking the most frustrating mystery in science, the fundamental anatomy of the atomic nucleus. In the 1920s, the atomic model was deceptively simple. Heavy, positively charged protons clumped in the center, while lightweight, negatively charged electrons orbited the outside like planets around a sun. But the mathematics of this model were a complete disaster. Physicists were kept awake at night by 2 glaring anomalies. First, the mass anomaly. Take helium. It has an atomic number of 2, meaning it possesses 2 protons, yet its atomic weight equaled 4 protons. Where was the extra mass coming from? To fix the math, without altering the electrical charge, scientists duct taped the theory together with a clunky workaround called the nuclear electron theory. They hypothesized that helium's nucleus held 4 protons for mass, but trapped 2 nuclear electrons inside to cancel out the extra positive charge, netting a weight of 4 and a charge of 2. But the spin of the atom proved that this duct tape was never going to hold. Subatomic particles possess an intrinsic quantum property called spin, with both protons and electrons having a spin value of 1/2. Basic math dictates that an even number of half-spin particles totals a whole number, while an odd number totals a half integer. Nitrogen-14 has a mass of 14 and a charge of 7. Under the clunky old theory, it would need 14 protons and 7 nuclear electrons, meaning 21 total particles. 21 is an odd number, so nitrogen's total spin had to be a half integer. But when experimentally measured, the spin of nitrogen was exactly 1, a whole number. The nuclear electron theory was mathematically impossible. The nucleus was fundamentally broken. Rutherford, with his terrifying physical intuition, had actually predicted the solution in a 1920 lecture. He declared there must be a third undiscovered particle, a missing piece with the exact mass of a proton, but with a neutral, 0 electrical charge. He called it a neutron. It was an elegant theoretical solution that would perfectly fix the mass and spin anomalies. But finding it experimentally, that became a 12-year nightmare for James Chadwick. He spent over a decade hunting a ghost. Every tool in the 1920s physics arsenal relied entirely on electrical charge. Charged particles like alpha particles or electrons rip electrons off air molecules, leaving visible trails of condensation in cloud chambers or triggering electrical pulses in Geiger counters. But the neutron? 0 charge. It doesn't interact with electrons. It doesn't ionize air. It leaves absolutely no trail, and it is entirely invisible to detection tools, passing straight through solid matter without a trace. Year after year, Chadwick bombarded elements with radiation, desperately searching for anomalies, and found absolutely nothing. A decade of his prime scientific life, hitting dead end after dead end. Then, the breakthrough finally arrived in 1932, and it started in Germany. Walther Bothe and Hans Becker were bombarding the light element beryllium with alpha particles emitted by polonium. They noticed a highly penetrating radiation shooting out. Radiation so powerful, it passed straight through thick sheets of lead. Unable to see it bend in magnetic fields, they assumed it was just ultra-powerful X-rays or gamma rays. The story then shifted to France, to the brilliant husband and wife team of Frederick and Irene Joliot-Curie, the daughter of Marie Curie. They recreated the German experiment, but placed a block of paraffin wax directly in the path of the mysterious beryllium radiation. Paraffin wax is incredibly dense with hydrogen atoms, essentially a dense wall of solitary protons. To their absolute shock, the invisible radiation slammed into the wax and knocked protons flying out the other side at massive speeds. The Joliot-Curies published a paper claiming that ultra-high energy gamma rays had struck the wax, knocking protons out via Compton scattering. When Chadwick read this paper in his Cavendish office, he literally could not believe his eyes. He took the journal to his mentor, and Rutherford uncharacteristically shouted, "I do not believe it." They didn't believe it because it violently violated the basic laws of kinetic physics. Gamma rays are massless photons of light. A proton is a heavy, massive boulder of a particle. The French claim was like stating you could hit a bowling ball with a flash of light, or a ping pong ball. and send it flying across the room at 100 miles an hour. It takes mass to move mass. Chadwick instantly realized that the Joliot-Curies had completely misinterpreted their own data. They hadn't found a super gamma ray. They had stumbled right over his ghost particle. The beryllium radiation was a stream of heavy neutral neutrons. The Joliot-Curies held the skeleton key of the universe in their hands and failed to recognize it. Dropping absolutely every other project, Chadwick worked feverishly late into the night, assisted by his colleague Norman Feather. He built an elegantly austere apparatus. Inside a small evacuated metal cylinder, he placed a tiny piece of polonium, a machine gun shooting alpha particles, next to a disk of pure beryllium. The resulting nuclear reaction spat out the invisible neutrons, which shot out of the cylinder and slammed into a block of paraffin wax, knocking out the heavy protons. But Chadwick added one crucial step. He placed a highly sensitive ionization chamber right behind the wax, hooked up to an oscilloscope. When the knocked-out protons flew into the chamber, he could measure their exact travel distance and energy. It was like playing a game of pool in the pitch dark. The neutron was an invisible cue ball. You couldn't see it, but when you heard a massive crack and saw the 8-ball, the proton, go flying into the corner pocket, you could measure its exact speed and trajectory. Using the laws of conservation of momentum, Chadwick mathematically calculated the exact weight and speed of the invisible cue ball. He mathematically trapped the ghost. He proved undeniably that the incoming radiation possessed a mass of approximately 1.00067 daltons, slightly heavier than a proton. It was not massless light, and because it left no track, it was electrically neutral. He had finally found Rutherford's missing particle. In February 1932, a mere few weeks after reading the French paper, he published his findings in the journal Nature, using the incredibly modest, almost aggressively understated title, Possible Existence of a Neutron. It was the understatement of the 20th century. He had just rewritten the fundamental structure of the physical universe, earning the 1935 Nobel Prize in Physics, a prize the Joliot-Curies tragically missed out on due to their misinterpretation. But the neutron was not just a scientific marvel, it was a cosmic trigger. Before 1932, probing the nucleus required shooting positively charged alpha particles at it. But a target nucleus also has a positive charge, creating a massive repulsion known as the Coulomb barrier, like pushing two north poles of a magnet together. A heavy atom like uranium, with 92 protons, possessed an electrical force field so strong that alpha particles simply bounced off. The heavy nucleus was an impenetrable fortress. But the neutron? It has zero electrical charge. It does not feel the Coulomb barrier. You can gently slide a neutron right into the heart of the heaviest elements in the universe, and the atom will simply swallow it up. When uranium swallows an extra neutron, it becomes highly unstable. James Chadwick's invisible projectile was the single mechanical key that made nuclear fission, and subsequently the atomic bomb, physically possible. In 1935, holding the Nobel Prize and ultimate job security at Cavendish, Chadwick shocked the scientific establishment by walking away. He moved to the rundown secondary institution of the University of Liverpool. Why? Because he and Rutherford suffered a massive ideological fracture. Rutherford stubbornly believed in little science, clever men using string and sealing wax on tabletops. He despised spending vast sums on industrial-scale machines. But Chadwick had seen the future in America, Ernest Lawrence's newly invented cyclotron. This massive circular particle accelerator used giant electromagnets to whip particles to unprecedented speeds. Big science had arrived. Rutherford flatly refused to fund a cyclotron at Cambridge, dismissing it as an American gimmick. So, when Liverpool offered Chadwick the Lyon-Jones Chair of Physics and promised support for a cyclotron, he left his mentor behind. Liverpool was a logistical nightmare. The facilities were antiquated, running on direct current electricity instead of alternating current. The university's promised funds fell violently short, forcing him to constantly scrounge for grants. In an incredible act of devotion to the future of physics, Chadwick took $8,243 of his own Nobel Prize money, almost the entire sum, to finish paying for the 50-ton magnet and the massive vacuum chamber of the 37-inch cyclotron. And his motivation? It was deeply humanitarian. He sat on multiple cancer investigation committees and firmly believed that intense neutron beams and artificial radioactive isotopes could become revolutionary, life-saving medical tools. He was pioneering nuclear medicine, pouring his personal fortune into a massive instrument of healing. By July 1939, his cancer-fighting machine was fully calibrated and operational. But in September 1939, Hitler invaded Poland. World War II began, and Chadwick's humanitarian dream was instantly, violently hijacked by the military-industrial complex. Just months earlier, German chemists Otto Hahn and Fritz Strassmann made a terrifying discovery. When bombarded with Chadwick's neutrons, the uranium atom didn't just absorb the particle, it violently split in half. It fissioned. Lisa Meitner and Otto Frisch published the theoretical proof that this process released a massive, unprecedented amount of energy, along with 2 or 3 extra neutrons. A runaway, exponential chain reaction was possible. Initially, elite scientists like Niels Bohr assumed a bomb was a practical impossibility. Natural uranium is mostly U-238, an isotope that quenches the chain reaction. You needed the rare, lighter, U-235 isotope, and physicists falsely assumed it would take tons of solid U-235 to reach critical mass, making it too heavy for any airplane. They believed it was a 50-year engineering problem. But in March 1940, the devastating Frisch-Peierls memorandum changed everything. Rudolf Peierls and Otto Frisch ran the complex math and discovered that the critical mass for a pure U-235 sphere wasn't measured in tons. It was measured in kilograms. A sphere the size of a grapefruit could unleash the explosive power of thousands of tons of TNT. The British government received this memo and formed the top-secret Maud Committee to verify if this horrifying theory was actual reality. They turned directly to James Chadwick because he sat in Liverpool with the exact machine needed to test the math. A brand new, fully operational 37-inch cyclotron. His terrifying task? Measure the exact nuclear cross-sections of uranium-235. He had to measure the effective target area of the incredibly tiny nucleus to determine the exact probability of a fast-moving neutron hitting it and causing a fission. If the probability was high, the bomb worked. The conditions under which he extracted these numbers were pure apocalyptic tension. In early 1941, Chadwick's team ran the most delicate subatomic measurements in human history, while the Luftwaffe mercilessly bombed the city of Liverpool into dust. The relentless Nazi blitz caused shockwaves so intense that the heavy glass windows of the physics department constantly shattered. Unable to keep replacing them, they boarded up the laboratory with heavy cardboard. Imagine the sensory reality. Staring at an oscilloscope, measuring the exact mathematical probability of atomic annihilation, while the walls of your laboratory physically shake. The city burns outside, and freezing wind violently flaps through cardboard windows. And it was there, in the shivering darkness of the spring of 1941, that the numbers proved undeniable. The first Peierls calculation was entirely correct. A fast neutron chain reaction was not a theoretical fantasy. A nuclear bomb was entirely, practically feasible. For a man who pursued physics purely to understand the quiet elegance of nature, The solid math was the absolute final end of his peace of mind. Sitting alone in his shattered office, Chadwick became the first human being on Earth to hold the empirical mathematical proof that humanity possessed the capacity to completely annihilate itself. He later confessed the crushing weight of that exact moment. I realized then that a nuclear bomb was not only possible, it was inevitable. Everybody would think about them before long, and some country would put them into action. He continued, revealing his profound despair. And I had nobody to talk to. I had then to start taking sleeping pills. It was the only remedy. I've never stopped since then. His agonizing isolation was absolute, and the countdown to Trinity had officially begun. The psychological burden was unfathomable. But the raging war dictated that he could not stop. In July 1941, James Chadwick was chosen to write the final, definitive draft of the Maud Report, the blueprint for the atomic age. He compiled all the theoretical physics, his own hard cross-section data, and all the engineering estimates for how to separate the U-235 isotope into one cohesive, terrifying document. He stated unequivocally that a uranium bomb was practical, that it could be built in time to affect the current war, and that it would produce an explosion of unprecedented catastrophic scale. Authored in the quiet, agonizing precision of Chadwick's style, this was arguably the most consequential document of the 20th century. In October 1941, a copy was handed to Vannevar Bush, the head of the American scientific effort, who took it directly to President Franklin D. Roosevelt. Before this, the American nuclear program was dragging its feet. Disorganized, underfunded, and highly skeptical. The MAUD report was the spark that ignited the gasoline. It was James Chadwick's empirical data screaming across the Atlantic. This will work, and we must build it before Nazi Germany does. It essentially kickstarted the multi-billion-dollar juggernaut that became the Manhattan Project. But Britain quickly realized a harsh reality. A financially drained country, completely under siege, simply could not hide a massive, power-hungry uranium enrichment plant from German bombers. So, in 1943, Winston Churchill and FDR signed the Quebec Agreement, formally merging the British nuclear program, codenamed Tube Alloys, with the colossal American Manhattan Project. The man appointed as the supreme scientific diplomat, the head of the British mission to the United States, was James Chadwick. Sent over under the incredibly thin, secret code name James Chaffee, he was thrust into the highest echelons of military and scientific power, reporting to General Leslie R. Groves of the U.S. Army Corps of Engineers. Groves was a bulldog, notoriously abrasive, deeply suspicious of foreigners, extremely protective of his compartmentalized security rules, and he generally despised the British. He clashed violently with almost every brilliant, egotistical scientist he met, from Leo Szilard on down, viewing them as arrogant children playing with toys. So how did a painfully shy boy from Cheshire handle a furious military general? Through a profound, counterintuitive superpower, Chadwick possessed an utter lack of ego. Surrounded by posturing prima donnas who constantly chafed under strict security rules, Chadwick didn't play the political game. He was quiet, rigidly disciplined, fiercely objective, and simply presented the unvarnished facts with absolute integrity. Groves, who valued blunt honesty above all else, recognized a kindred spirit and formed a deeply trusting friendship with him. In a project defined by extreme paranoid secrecy, Groves made an astonishing, unprecedented exception. He granted James Chadwick, the only civilian and non-American, full, unhindered access to almost the entirety of the Manhattan Project's research, data, and sprawling production facilities, with the sole exception of the Hanford plutonium plant. Groves trusted this quiet British scientist more than he trusted most of his own generals. By 1944, Chadwick moved his family, including his twin daughters, previously sent to Canada for safety, down to the secret laboratory at Los Alamos. There, he oversaw the integration of brilliant British scientists like Rudolf Peierls, Otto Frisch, and William Penny into the most critical areas of bomb design. He navigated housing disputes, salary adjustments, clashing egos, and massive geopolitical strategy, all with the exact same unshakable tenacity he used to survive a freezing German POW camp. All of this quiet, agonizing war culminated in the dark desert of New Mexico. July 16, 1945. The Trinity Test. Chadwick sat in the observation bunker, looking out into the void, waiting for the countdown. And in the mechanics of the weapon he was about to witness, there lay a profound, almost poetic, scientific symmetry. To make the implosion-style plutonium bomb work, the exact type tested at Trinity and later dropped on Nagasaki, the scientists needed a way to flood the core with neutrons at the exact microsecond of maximum compression to kickstart the chain reaction. They needed a neutron initiator, specifically the Urchin initiator. At the very center of the bomb, they placed a tiny pellet of polonium and a tiny shell of beryllium, kept strictly separated. When the explosive lenses fired and crushed the core, the polonium and beryllium slammed together. The polonium emitted alpha particles, which struck the beryllium, which instantly released a massive burst of neutrons. It was the exact same mechanism, the exact same nuclear reaction that James Chadwick had used on his quiet lab bench in Cambridge in 1932 to discover the neutron in the first place. He had used it to uncover a secret of nature. Now, it was the detonator for the most destructive weapon ever conceived. Standing in the desert, he watched the terrifying culmination of his own tabletop experiment illuminate the new world. William L. Lawrence, a New York Times reporter attached to the project, was watching Chadwick that day. He later wrote that, "Never before in history had any man lived to see his own discovery materialize itself with such telling effect on the destiny of man." Shortly after, the bombs fell on Hiroshima and Nagasaki. Hundreds of thousands were incinerated, and the war ended in absolute devastating victory. Chadwick received a knighthood in 1945 for his services, becoming Sir James Chadwick. But the moral fallout was only just beginning. When he finally returned to his post in Liverpool in 1946, he was a fundamentally changed man. Sir James Mountford, the Vice-Chancellor of the University of Liverpool, noted in his private diary that he had never seen a man so physically, mentally, and spiritually exhausted. Mountford wrote that Chadwick had plumbed such depths of moral decision and suffered almost insupportable agonies of responsibility. He had built the bomb out of a cold, pragmatic terror that Nazi Germany, led by scientists like Werner Heisenberg, would build it first and enslave the world. Yet, once the true horror was visible in the ashes of Japan, many atomic scientists, like J. Robert Oppenheimer and Leo Szilard, immediately pivoted to fierce pacifism, advocating for international control and universal atomic disarmament. They desperately wanted to put the genie back in the bottle. But Chadwick did not join the pacifists. Despite the agonizing guilt that required him to swallow sleeping pills every night, he pivoted directly into the harsh realities of the emerging Cold War. He became an outspoken, fierce advocate for the United Kingdom developing its own, fully independent nuclear weapons stockpile. This sparked a bitter, massive public clash with Patrick Blackett, another Nobel laureate, who vehemently argued that a bankrupt Britain should remain neutral and avoid an arms race. Chadwick understood the physics of the atom, but through the crucible of war, he had also come to understand the dark physics of human nature. Having sat in the highest-level strategy meetings in Washington, D.C., and having witnessed the aggressive maneuvering of Joseph Stalin, he knew the genie could not be contained. He knew the Soviet Union would eventually build their own bomb, which they did far sooner than expected in 1949. To Chadwick, unilateral disarmament wasn't nobility. It was suicide. He used all of his accumulated political capital as a Nobel laureate and the hero of the MAUD report to push the British government to build the bomb, effectively establishing the UK's independent nuclear deterrence. Having won the debate, he recognized the toll had been too high. His time as a frontline researcher was over. He had given his best scientific years to hunting the neutron, and his best emotional years to the war effort. In 1948, he stepped away from the laboratory, returning to Cambridge to become the master of Gonville and Caius College. Yet, peace constantly eluded him. His relentless, autocratic push for academic rigor ruffled the feathers of the established dons, sparking a bitter political battle known as the Peasants' Revolt that heavily shadowed his final years. Though, in a remarkable twist of fate, it was during his tenure as master that two fellows at his college, Francis Crick and James Watson, discovered the double helix structure of DNA. The scientific revolution simply continued swirling around him, shifting from the nucleus of the atom to the nucleus of the cell. He fully retired in 1958 to a quiet cottage in North Wales with his wife, later moving back to Cambridge in 1969 to be closer to his daughters. Through the guilt, the politics, and the bombs, he remained a strict, lifelong atheist. He never sought religious comfort or absolution for the immense burden he carried, facing the terrifying reality of the nuclear age with unblinking secular stoicism. Sir James Chadwick died quietly in his sleep on July 24, 1974, at the age of 82. His was a life defined by the most incredible cinematic contradictions. The painfully shy working-class boy who accidentally stumbled into physics became the most trusted confidant of presidents and generals. The scientist who poured his fortune into a machine to cure cancer ended up providing the exact mathematical blueprint for the weapon that could end human civilization. It perfectly encapsulates the double-edged sword of scientific discovery, how the pursuit of pure knowledge, completely detached from morality, inevitably collides with the deeply flawed reality of human conflict. It leaves us with a profound, lingering sense of the sheer fragility of history. Consider this. Long after the screen goes dark, what if a young, impoverished James Chadwick had just been a tiny bit braver at his university enrollment in 1908? What if he had simply cleared his throat, spoken up to the clerk and said, "Excuse me, I'm actually supposed to be in the mathematics line"? How much longer would the neutron have remained an invisible ghost? Would the atomic bomb have been delayed by a year or a decade? Does the fate of the entire modern world, the shadow of the Cold War, and the geopolitical map we survive under today hinge entirely on the social anxiety of a single 18-year-old boy? It is a haunting thought. If this descent into the shadows of history sparked a realization for you, please subscribe to Legendary Lives Unveiled, leave a comment, and share this video with someone who loves stories where the hidden corners of science and history violently collide. Your interaction is the only way we can continue pulling back the curtain on the fascinating, terrifying realities of history's greatest figures.